Hi everyone. Today we will review chapter 18, 19 and 20 by solving the practice exam. So in the exam there will be 20 questions and they are all multiple choice problems. And today I will solve 13 multiple questions which kind of serves as a practice for the real exam. So let's get started. The first question, it asks about two charge objects are separated by distance d. The one charge is larger in terms of magnitude than the second one. Which statement best describes the force exerted on each object? So it asks about the Coulomb's force, electrical force between two charges. Let's say one is larger, let's say 2q. Another one has, say, q. And it doesn't say anything about the signs of the charges, but the Coulomb force, electrical force on charged particles will be exact same magnitude, but in opposite direction. So if there's a force on 2qf, there must be same magnitude, but in opposite direction on the q. So the answer is going to be C, because if in a system the forces must cancel. If you think as a uniform system, like if the forces are different, net force is going to be non-zero, and the particle system will move by itself. That just doesn't make sense, right? So if the reaction is a reaction in opposite direction at the same magnitude. Two neutral atom always has the same number of positive and negative charges, and the positive charges are protons and negative charges are electrons. So it will be D. Neutrons are neutrons, they don't have any charge, net charge. So for 3, a parallel plate capacitor is connected to a battery and becomes full charge. The capacitor is then disconnected and the separation between the plates is increased in such a way that no charge leaks off. The electrostatic potential energy stored in the capacitor has, okay, you have a Q and minus Q, so you have a C and distance is D. Okay, now let's make it 2D. You don't have any change in the Q. The potential energy for the capacitor you can write in terms of 3 different ways: Q times V, or Q squared divided by C, or V squared times C, because Q charge equals V times C, right? And you can play with them around. But here what you know is the Q doesn't change, but you know how much C changes. Capacitance equals epsilon naught area divided by D, right? And for the second one, say you make it 2D, the capacitance is going to be half of it, the initial one, right? If you call it C, it's going to be half of it. So then you know the Q doesn't change, so that you can use this equation, right? Oh, sorry, this is not gonna be C squared. It's going to be just C. So in the first one, let's say C, and the second case, the distance is gonna be 2D, and the capacitance is gonna be C over 2. C over 2, and if you put it up, it will be 2 times Q squared divided by C. So when you increase the distance from D to 2D, the capacity is gonna be half of it, but the energy is inversely proportional with the C if the Q is constant. So that's important. So with that, because of that, the capacitance is gonna, the energy is gonna increase. So another approach is like you can think as an energy density. The energy density, electron is proportional with Q divided by A epsilon naught electric field in the system. Okay, the energy, can I write this energy, is the unit energy density times the volume, right? So if the Q is constant, electric field is gonna be constant. But if you increase the volume, then actually the total energy increase. So that's another approach you can use. For 4, the resistance of a wire is proportional to both its length and cross-sectional area. So it asks about the cross-section and length. So the resistivity is proportional with the resistance is proportional with the resistivity times length divided by area. If you increase the area, you will have less resistance. The charge is gonna have more area to flow. So you can think in terms of that. So it's proportional with the length, and inversely proportional with the cross-section area. So that's B. The others are inverse proportional length. None of them are correct. 5. For an electron moving in the direction of the electric field, you have an electron minus charged moving in the direction of the electric field. You have an electric field and its velocity in the same direction. So it's moving in that direction. So it asks about what's true about its potential, energy, and electric potential. So because being negatively charged, electric potential and electric potential energy will be opposite, they'll have opposite relation because energy is just Q times V, right? So it's a negative charge for electron. If you write just minus EQ, then you will have minus negative relationship between, opposite relationship between V and U. Let's think about this problem. So when you have an electric field in that direction, the force is gonna be this way, right? Or you can call it like this in a parallel plate. This is a high potential and this is gonna be low potential, right? Because the electric field is that way. So the electron is moving to low potential. So potential will decrease. Potential will decrease, but the potential energy will increase. Okay, it will be A. For 6, a parallel plate capacitor has a plate area separated by a distance of 1 millimeter and the potential applied by 6 volt. And what's the electric field? Potential is just E times distance, electric field times distance. Potential is 6 volt. E times D is 1 millimeter, 10 to minus 3 meters. So electric field is going to be 6,000 and Newton Coulomb. Here we did as volt divided by meter, but it's gonna be the same. 5 Coulomb charge is 10 meters from a small test charge. What's the magnitude of the force experienced by a 1 nanocoulomb charge placed at the location of the test charge? You have 2 charges. One is 5 Coulomb, is separated 10 meters away, and you put 1 nanocoulomb. And what's the force on that? Like magnitude of the force? It's K Q1 Q2 divided by R square. 9, 10 to 9 is the K. Q1 is 5 coulomb times 1 nanocoulomb divided by 10 meters. So this will be 45 divided by 10 is 4.5 Newton. 8, a light bulb operating at 110 volt draws 1.4 amp. And what is the resistance? E divided by I. 110 divided 1.4. Then it's going to be 78.6. 9, which of the following will definitely increase the capacitance of a parallel plate? So let's remember the capacitance is epsilon naught. It's proportional with the area and inversely proportional with the distance. So increasing, if you want to increase the capacitance, you must increase the A and you must decrease the D distance. Increase the area, decrease the plate separation. So it will be B. I mean, you can ask, what about E, increasing the plate area or increasing the plate separation? So you don't know how much you change. So it says it definitely increase. So because of that, B is going to definitely increase the capacitance. 10, a total of 2 times 10 to the 13 protons passing at a given point in 15 seconds. What's the current? Let's remember the definition of the current. It's the charge per time. So, but it's giving the protons. So we need to convert to the coulombs. It's 1.6 10 to minus 19 coulomb. And it's passing in 15 seconds. So you have 3.2 divided by 15, 10 to minus 6 amp. And 3.2 divided by 15 is going to be 0.21, 10 to minus 6 amp. So this is microamp. That answer is going to be C. 11, an electron was accelerated from rest through a potential difference of 2000 volts. What's its speed? So let's say you have a plate, electrons are released from here and went to 0 volt from 2000. Oh, wait a minute. Electron is going to go the other way around. So electron must start from this way because electric field here, force is going to be this way. Anyway, it doesn't matter that much. The potential energy change is going to be delta V times Q, right? And the potential change is going to be 2000 times electron charge and will be equal to the kinetic energy. And the velocity is going to be 2 times 2000, the potential change. And the charge is going to 1.6 10 to minus 19. And the mass of electron is 9.1 10 to minus 31 kilograms. And the square root of this. Then, so you can, let's see, you have 4 times 1.6 divided by 9.1. You have 10 to the 3, 10 to minus 16, and 31 is 10 to the 15. Let's do 10 times 10 to the 14. So this will be 10 to the 7. So then this product is going to be square root of 4 times 1.6 times 10 divided by 9.1. It's going to be 265, 10 to the 7 meter per second. So then this will be A. Two capacitors, one a 4 microfarad capacitor and other 6 microfarad, are connected in series. If a 90 volt touch source is applied to the capacitors as shown in the figure below, find the voltage drop across the 4 microfarad. So this is 4 microfarad and this is 6 microfarad. So when you have a parallel series capacitor, they will have the same charges, right? And as you connect the voltages, this has a potential V1 and V2. So V1 plus V2 equals 90 volts. And you can call Q, okay, the Q is, the capacitance C1 is 4 microfarad. And other one is 6 microfarad. So if you do this Q and you have 1.4 plus 1.6, and you have a 1 microfarad unit for the capacitors, 90 volt. So, and this will be Q 1 microfarad, but by multiply by 3 and multiply by 2, it's going to 5 divided by 12, right? And 90 volt. Then Q will be 90 times 12 microfarad divided by 5. Then it asks about what is the potential on 4 microfarad, which is V1. So V1 is Q divided by C1, right? And we found the Q, 90 times 12 microfarad divided by 5. C is 4 microfarad. Then you see the units are gonna cancel. So V1 is 90 times 12 divided by 20. So 90 times 12 divided by 20 is going to be 54 volt. So I didn't find a Q, a final Q here because it doesn't need it, because I know it will cancel with the microfarad. Let's make it easier. If you want, you can find the total Q and then calculate the potential V1. Okay, last question. A toaster is rated for using average power 800 watts at 120 volts. What is the resistance of the heating element? So you have element is a resistor, R basically. The power is going to be I times V, right? And its average power is I RMS times V RMS, right? So I mean, this is kind of if you go back to the when this is general representation of the power, right? And any point of the power, let's say in terms of time, when you have a AC current, you have I naught sine omega t, let's say, and you have a V naught sine omega t, and any instant point, any point, so you have this power, right? But when we talk about the average, if you track 10 called the P average, then this will gonna be half of the instantaneous power. Okay, so, and then if you remember I naught in terms of IRMS, IRMS is I naught divided by square root of 2, or 0.707 I naught. Same for the potential. So for I naught, you can write square root of IRMS. So V naught, you can write square root of V RMS. And when you divide by 2, square roots and 2 are going to cancel, and you have IRMS times VRMS. It's about what's the average power. So then you can write I in terms of V and resistance. I is V divided by R. So R is going to be V squared divided by 800 watts. So you have 120 squared divided by 800. That's going to be 18 ohms. So basically, you don't have to do all these derivations, just you can go from here and here. Here I would like to show more background. So I show this how the RMS value is related to instantaneous current and potential. So then this is 18 ohms. So that's all for this practice exam. Good luck for the exam, and let me know if you have any questions. Please feel free to ask for additional office hours to me or the TAs, and good luck.